software engineering and quantum computing. And one moment. Okay, and basically the plan is as follows. So the talk will probably take 1 hour, 15 minutes, 1.5 hours. So first I will talk about like motivation, like why we even want to make it easier to do computational research and like quantum computing. Why do we need software for that? Then I will share a couple of like general tips how to like make it easier. Then I will go into workflows and explain a little bit what are workflows, what are the design principles that we have at Zapata when like creating our software. Then go into non-workflow like Python interfaces, which is also like very useful for this kind of problems, and that will be it. So, okay, so a little bit information about those who don't know. So Zapata Computing is a startup creating software for quantum computers based in Boston. Orquestra is our product, our platform. Orquestra is a workflow management system designed for running calculations on quantum computers. And my name is Michał, and I work as a quantum software engineer at Zapata. And what I do, I write mostly scientific software for Orquestra. And so in this talk, I don't want it to be a sales pitch of Orquestra. I want it to be like useful for people listening. So I will talk about Orquestra rather as an example of, because that's the workflow system that I know best. So I'll rather use it as an example of how it might look like. But I will try not to go too much into details of how exactly Orquestra works, just a little bit to like give you the general understanding. Okay, so let's begin with some motivation behind, using workflows and like some problems that we face in computational science. So I wanted to share a couple of stories with you. So the first story is when I was doing my bachelor and I was running some simulations. At some day, my MacBook broke, and I had to go on with the research. But I gave my computer to service for fixing, so I didn't have it for a week. So I looked whether I have any other options, and the best option I had was a Raspberry Pi that I had in my home. So I uploaded some of the code to Raspberry Pi. Fortunately, I had a backup of all the data, and I knew I won't be able to run any simulations, but I was running more like data analysis. And when I took all the data that I generated before and I started analyzing it turned out that the data is like absolute garbage. I mean, it didn't make any sense at all. So I started, digging into it and trying to understand what happened, because the code was exactly the same that I was running a day before on my MacBook. And it turned out that Raspberry Pi was running on Linux and MacBook was running on Mac OS, and that the sort function, when I was like loading files and sorting the names, the sort function worked slightly differently. So I got my files in different order on Linux and in different order on MacBook. So basically I was looking at wrong files at wrong moment, and I was like merging these files in a wrong way. And that's why I got like very stupid results. So another story, another thing was when also that was for my master research. I was running pedestrian simulations, and I was looking for a way to keep track of different simulations and different results. So what I did, I had this brilliant system where in the name of each file with results, I was putting parameters of my simulations in there. So for example, if my like population size was 5, there was like run dash pop size 5 dash something else. So the system was great and it was flawless until I realized it's not. So the issue with that was that when I started the simulation and then I realized there's a bug in the code. So I fixed this bug and I restarted the simulation. And then I realized that actually I could add this another feature to the simulation so it will run faster. So I stopped the previous one and started a new one, and I tweaked this in the code. And then, after the process, I repeated it a couple of times. Finally, I had no idea of which run is done with which version of the code. And I couldn't say whether, whether these results are done with the code with the fixed bug or with the bug. So I had to basically rerun everything from scratch because that was the only way to tell that the results are valid. Another story was from the time when I was working at Estimate, and there were 2 teams. I was in one of them, and we faced like a similar problem. So we decided that, well, it makes sense to join our forces and work together on solving this problem. They had developed one method, one algorithm, we have developed another one, and we wanted to compare them and see which one works better in which cases. But it turned out that it's not that easy to compare it because we couldn't use their data because they had different data format. Because they were storing data in an SQL database and we were storing data in CSV files. And there are like other, issues with like compatibility of our data. And it turned out that it took us some time before we were able to actually work out a way to share the results in a compatible way and to compare our methods. And the last story I wanted to tell you is, I call it like my greatest failure, because that's how it felt at the time. So when I was at Estimate, when I joined it, I was assigned to rewrite code from MATLAB to Python because we had an algorithm running in MATLAB. And I did that. And then we worked on that algorithm for quite some time. It didn't work perfectly, so we had to add some additional features, like make it more complicated, until finally it actually worked well. Then we launched the product. It was good. It was working. We started to work on some other projects. And we came back to this algorithm again after like about a year, because we knew that there was something wrong with this algorithm, and it seemed that that we missed something in how it works. So when we started digging, it turned out that in one place of the code, when I was rewriting this code from MATLAB to Python, I changed the sign, and I just plus from minus in one equation, and it resulted in like really big, like much worse performance. So after I fixed it, it turned out that the algorithm, as it should be, worked well enough so that we didn't need to do any improvements to that. So basically, I felt really bad about it because due to like my one mistake, like a couple of people working for a couple of months just like wasted that effort, because if I hadn't, the algorithm would work and we could just like do something else with that time. And well, there are a couple of lessons from these stories that I learned, which I think illustrate pretty well why doing computational research is hard and what are some challenges. So the first lesson actually goes to the last story. So if the code we had was not one huge Python script, but rather a set of like modular functions with unit tests, we probably wouldn't go into these troubles if we had even like unit tests as all. Another thing was that we were working, another reason why it didn't work, because we were under pretty big pressure of time, and we committed to create this algorithm before we even had, you know, a good idea, understanding of what's the problem. Okay, and well, that's like it's better to, you know, promise something once you have a working prototype rather than just an idea how it might work. Another thing is like, you know, the operating system you are using matters. That like keeping track of your calculations is hard. It's harder than it seems. Keeping track of your code and version of your code is hard as well. And you know, that I also learned that working with other people requires coordination, and not only just like talking with them, but actually making sure that, you know, if we know that at some point we'll want to use our code, like we use someone else's code, we need to make sure we will be able, and that their code is compatible with ours. Okay, so the challenges that we face in computational sciences are that there's like a couple of them. They're like long runs. So, you know, if your simulation is running for a day or for a couple of hours, it's like hard to manage. One way to manage, to like handle it, is running calculations in parallel, but then it requires handling this parallelization, and that's always not always easy. Then interoperability. In bigger projects, you might be using like different libraries that have different dependencies, and in the end, you might end up in a situation where one library requires some package to be version 2 and the other requires it to be version 3, and well, that's pretty hard thing to solve. But also like other things are like keeping track of your work, and like sharing your work with others is also something that people struggle with. Maintaining the code in general is hard. And another challenge is that sometimes people had wrong expectation, because especially in machine learning and in quantum computing, I think that a lot of work that you have to put is in the pre-processing, and you know, it's not actually the core of the things that you want to do. And you spend like 90% of the time like just cleaning the data or like preparing it, and then only 10% working on the algorithm, and it might lead to some frustrations. So here are a couple of things that are like additional challenges that are specific for quantum computing. And this is the fact that we have different frameworks. So like Qiskit, Pikewill, Cirq, and others. And they are not always compatible. Also, different frameworks use different conventions in terms of, for example, numbering the qubits, or how you structure some data. Another thing is that connecting to QPU via cloud, well, it's not super complicated, but it might lead to some issues, for example, with queuing, and you have to handle that in your code. Also, QPU interoperability. So, you know, there is like one QPU might be using different gate set than the other, or might have different architecture. So you cannot easily like move one algorithm from, you know, one QPU to the other. Also, like quantum computing is probabilistic, so it also makes it sometimes harder to debug. And the science is dynamic. So an example of what I mean by this is that we, you know, at Zapata, like, I don't know, like a couple of years ago, we didn't know that the measurement problem is so important, and that you actually need that many measurements to get unreasonable results. And once we learned it, it turned out that, well, we need to have pretty elaborate methods for dealing with that, as we recently published a paper about it. But from the software perspective, it actually might change, you know, the focus of the software, because you think that the measurement is like a trivial part, so you don't even bother to, you know, write a good module for handling measurements, and then suddenly it turns out that actually measurement is a huge problem and you need to spend a lot of time working on just that. Or bar and plateau is also a good example of something that people didn't realize that is a huge problem, but it turns it is. So initialization of parameters is much more important than people thought a couple of years ago. Okay, so these were like motivation, so a couple of problems that people face, but what we can do about it. So as I mentioned, like one of the things is, versioning and using version control like Git. I don't imagine like writing code without Git nowadays, but also keeping track of all the versions of the packages that you're using. Especially in quantum computing, these frameworks really evolve pretty quickly, so it's important to know that. Automation, so there's this nice rule of thumb that if you do something once, then okay, you can do it manually. If you need to do it for the second time, okay, you can do that manually, but when you do it for the third time, it's probably worth to put some effort into actually automating it, because otherwise, like there is a huge chance that if you needed to do that 3 times, you might want to do that 4th time or 5th time. So it's just like worth doing that. Don't repeat yourself, like good software practice that not all scientific code actually obeys. Taking your time, as I said, like working under pressure of deadlines is not always a great idea, and sometimes just as like having a plan when you plan your work, just having a buffer to account for the like unknowns is a good idea to do, especially in research. Using Profiler. So Profiler is, for those who don't know, this is a tool which allows you to see how much time your program spends in like every function. So you can easily find the computational bottlenecks in your code using Profiler. And for example, I once had a script which was running, well, surprisingly slow. I ran Profiler, and it turned out that in one function, I think it was like calculating mean squared error or something like this. I was passing a list, Python list, instead of NumPy array. And just the operation of doing that on list was like super slow. When I switched to NumPy array, suddenly my code was running 2 or 3 times faster. And it took me, I don't know, like 20 minutes to actually find this issue with Profiler. In general, following good software practices is just like worth it. And another thing is that it's worth, sometimes we just like fix on like one idea, and we kind of really want to solve this problem, but we don't see a bigger picture. And just like talking to others and asking them for opinion, asking them for help, usually allows you to solve your problems much faster, and people sometimes forget about it. Good process and culture. So things like code review, having very clear research process. So here I mean that you always kind of do your research in the same way, and you store your results in the same way, so that there is like less space for confusion or mistakes. Pair coding. So this is a thing that like is counterintuitive, but actually, if you take another person and you write the code together, it might be much more efficient than doing it by yourself, even though they're like doing it, there are 2 people spending time on one thing that the first one in principle could do alone. But first, it leads to smaller number of mistakes because you have 2 pairs of eyes looking at the code. It leads to better ideas, 2 people. And also it's much easier to do code transfer, like knowledge transfer, because there are 2 people knowing this particular piece of code. So that's also worth considering. Learning to estimate duration of tasks. As I mentioned, not promising anything until you have working prototype, or at least you know what you are doing. Working with others, that's as well. And the last is you are not your code. So some people treat their code very emotionally, and they just, if someone criticizes their code, they take it very personally, and this is not a good attitude to have. If you have written like code which is bad, it's like doesn't mean you are, I don't know, a bad person or incompetent. It's just like this code is bad. So it really helps to have this like culture, like this elements in processing culture to make the research smoother. Okay, so that was, I would say, like general advice and like some general problems that we face. And now I would like to explain to you more about workflows, which was in the title of this presentation. So one moment. But before I explain you what the workflows are, I wanted to tell you about some design principles that we have at Zapata. Okay, one moment. Okay, so I will go to the chat and answer any questions afterwards. It's like I'm not sure like how much time do we have, how much time it will all take me, but I will definitely stick until all the questions are answered. Okay, so design principles. I hope that's okay. Okay, so design principles, that's like something we keep in mind when we are writing any software at Zapata. And the first one is extensibility. So we want software to be extensible, which means that like other people can easily build on top of what we have built. So the situation that might like often occurs that you find an open source project which solves the problem that you have, but actually it's like the interface, the input outputs are so different from what you need, the format of the data, that it's so badly documented that it's just hard to use, or it uses some weird dependencies. So we want to avoid it, and we want to make sure that like every piece of code that we write will be usable by others. Another thing is modularity, which means that we want to have all the elements like as well modular as possible, which means that they have as little dependencies on each other and as possible. So for example, you might have a case where you have like one huge script and you need to use something from library A and then from library B, but it turns out that actually the two of them like just don't work together. I mean, it just happens, like something crashes and you cannot do anything. So the idea of modularity is to be able to just have as little code in one place as possible, but also to have okay, I will give you an example later, but that's basically the modularity. So then reproducibility means that we want all the calculations that we run to be easy to reproduce by others and by ourselves in future. So if it turns out that there was a bug in our code, we want to be able to go back to that particular place where it happened and repeat all the calculations to make sure the bug didn't affect us, or if it did, like take some actions. And also scalability. Well, we want the software to be scalable, and you as a user shouldn't care about whether you run it on like a single computer or a cluster. And also you shouldn't care about whether you want to run it for like 1 parameters, 5 parameters, and 100 parameters. It should just like scale well. And of course, well, no one's perfect, and I don't claim that we meet all those principles like perfectly, but at the same time, this is like, I think these are good principles to like strive for. And this is something that workflows workflows are a good tool to do that. So how does a workflow look like? So this here is a simple graph showing variational and quantum factoring algorithm. And you can see that we start from a number, we then do pre-processing, then we get some clauses, and then we perform some optimization on these clauses. We get some samples, we do some post-processing, and then we get the result. So, and here is like the similar, graph for the only like the optimization step. And this is basically, workflow, which is, I don't know, like, a kind of proper definition, but workflow is a way to organize your process, your code in a way that you have some actions that are doing something and then passing the result to like another places where something is done with this data, and then another and another. I know, like, it's pretty vague, but I think you get the idea. To establish some language to make it easier to actually talk about these workflows, I would like to explain to you some elements of the workflows. So the first and like most basic element, I think, is task, sometimes called job. So a task is a place where you do something, whether that's, pre-processing or change. You can deal with that on like different granularity, but I don't know, like normalizing your data or cleaning your data or something else, or like calculating gradients or whatever. This can be a task. So then artifacts are kind of the objects that you pass between tasks. So if you have a task which is like create circuit, the artifact is the circuit, right? And you're going to pass the circuit to other tasks. And another thing are parameters. So parameters are also something that you like specify how given task should behave. So for example, parameter might be number of qubits, number of iterations, or I know, target, precision of some numerical calculations, and so on and so on. And the last one are resources. And resources are something that we kind of use for performing tasks, in the sense that, like, in case of Orquestra, the resource is usually a Git repository. But in some other workflow system, it might be, for example, a Docker image, right? So you want to run the same task on like different Docker images, so you kind of you can do that using different resources. Okay, so I want to make it like a little bit more tangible. So this is a graph showing how to perform VQE to calculate energy of a hydrogen molecule for like different bond like loops. And this is like some visualization of the workflow. So we start with bond length loop, which is like we basically loop over different bond lengths. And in each loop, we first create a molecule, then we generate some basically a geometry of this molecule. Then we get a fermionic Hamiltonian. We need to transform this into a qubit Hamiltonian, and then we can use qubit Hamiltonian for the optimization. And on the other hand, we also create a circuit. We generate some parameters. We have these initial parameters, and this is like an object that we pass to optimizer loop, and then we do optimization, and in the end we get results. This is like a simple workflow, and I would like to show you how a workflow looks like in Orquestra. So here there is an example. So you have to define the workflow somehow. Sometimes you can use an like graphical interface to just like draw those graphs and those nodes, but actually often you use YAML files for that. And I don't want to get into exact details of how this specific workflow works. I just want to give you like a general idea of how workflows work. So here we specify some resources. So you can see, for example, we specified that we want to use this repository and this specific branch of that, or like some other repository for other resources. then you remember, like we said, we are doing calculations for different bond lengths and actually using different methods. So here we loop over 3 different basis sets and many different bond lengths. And here we actually, for this like initial parameters, we actually calculate something. So as I said, like first we create this molecule, then we create some object, which is called, then we create Hamiltonian. And as you can see, one of the things that we get from the previous task is something called geometry, right? So this task gets as an input artifact output of the previous task, right? And then the next task, which is transform Hamiltonian, gets as an input Hamiltonian, which is generated by the previous task, and so on and so on. So then it turns out that like some of these artifacts are used like later in this workflow, and it's pretty convenient that you have all the pieces like separated from each other. So example of how the whole workflow looks like. And then example of how a specific task look like is here. So we have the transform Hamiltonian, and as you can see, it has some input artifacts, it has some parameters. So for example, which transformation we want to use. So in this case, like Jordan Wigner, like some which Docker image we want to use, and so on and so on. But this doesn't tell you like exactly how this task behaves. This is done in the task definition. So here we define what are the inputs and outputs of every task, and what the task is actually doing. So what it is doing, it's running a Python script, which is here. And this is like a little snippet of, this is a little snippet of code. And as you can see, we use OpenFermion package to perform transformation, either Jordan Wigner or Bravik-Kitaev, to transform the Hamiltonian, right, the operator that we got as an input. We also first need to load it and save it. And these are kind of like crucial steps, because in principle, we can just go into the workflow I just showed you, and we can replace this task with another task or another set of tasks, as long as it accepts the same input and provides the same output as this one. So if there is like another library which performs the same transformation, if I have written this code myself, as long as I can load this operator from JSON and then put it into a JSON, I'm good, and I can just use it in my workflow. So this shows this like idea of modularity, that you can just like take something out and plug in something else that does it better or differently, as long as it fits in the place. So here I wanted to also show you how running such workflow looks like. So this is actually for like a simple QA way, and you can see we have like several tasks, and we execute them one after another, and it's not really impressive, but the magic happens when we want to calculate multiple things at the same time with different parameters. So for example, let's say I want to check how it works for 3 different graphs and 3 different optimizers. So then I simply create it in the loop where I pass 3 different like parameters for creating graphs. And then in each loop, I added one template to test it with like a different optimizer. And with very little actually additional code inside my workflow, I am able to scale it and perform much more operations. And for me as a user of this workflow, it's extremely convenient because I don't need to think about all the details. And one thing that's regarding like the scalability point, is that it actually doesn't take much more time, because this took about 3 minutes, 15 seconds to run this code, while one moment, while running the previous one took 2 minutes, 50 seconds. So even though I'm performing much more calculations, actually the overhead is not that big. Okay, so let me reiterate on the design principles. So using workflows allows you to make your code, your project more extensible, because you can just, take workflow, for example, like someone else created, and like plug it into your workflow. So let's say if like someone created this like super complicated procedure for creating like an ansatz, and you need that ansatz, then you can just like take this whole other workflow and like plug it into your workflow, and you can use it easily. In principle, so these are things that, like, if the code is well developed and well structured, you can do that with like any type of code. But actually in this case, you don't even care like how the code of this other person looks like, because you only care that they pass you in the end like this one file, which is the file that you wanted. Again, it's modular because as I showed with this transform interaction operator task or whatever the name was, you can just like plug in something else. You can plug in like a different optimizer, and it doesn't require for you to change the whole thing. It's just like requires you to change this like one step. Reproducibility, well, many workflow, actually I will talk about it in a moment as well, but if the workflow manager you use keeps track of the runs, you can always go back and see which run was performed, like was calculated with like what parameters and so on. So it's like very easy to keep track of your maybe not very easy, but like easier to keep track of your calculations, parameters and everything, and also then like easier to actually reproduce them. And since in this particular instance, for example, we keep track of the specific repositories and branches, like we could also keep track of the commits that we used, and we can make sure that we are running this particular workflow with like this particular code version. And scalability, well, there are like two ways, for like two flavors of scalability. So one is horizontal and the other is vertical. So horizontal scalability is something I've showed you, that I can just like increase the number of parameters and it will run more tasks in parallel. And I don't have to deal myself with the parallelization. This is something that the workflow manager deals with. But the other type of scalability is vertical scalability, which basically means that I can assign different machines, different hardware for different tasks. So if I need, for example, for optimization, a very powerful, computer, because it's like takes a lot of computations to do that, I can say, okay, for this specific task, please run it on like, very powerful machine. And for other tasks that don't need that much power, I can just say, okay, like they should like use less memory. So then it's like easier to scale your resources for like specific tasks as well. And there are some additional benefits of using workflows. So the first one is that it makes it easier to keep experiment logic separate from the configurations and the parameters, because all the parameters are passed as as parameters into the workflow, and it's just like harder to make a mistake of hard coding something. It's just like more transparent in that way. The second thing, which I think is pretty profound, and I really started appreciating it, like the more I use workflows, the more I appreciate this, is that using workflows forces you to structure your thoughts, your work, your code in a way that like helps you thinking, because you cannot have kind of every piece being dependent of like every other piece in some vague way. You cannot just what you need is you will have, excuse me, I have to drink. So you will have, I'm sorry, I'm just like slightly confused. Lost my track. What I want to say. Okay, so using workflow actually like forces you to think about the structure of your code, about like how different parts like depend on each other, what data do you actually need to pass between all the parts, and well, it just like makes it much easier to manage. It makes it much easier to think about it. And also, as I mentioned, like workflow manager can automatically keep track of different things. So like parameters of time of execution, of time when you run it, and many others. So it has like this additional benefit of making it easier to manage your research. Okay, but you know, it's all great, but actually workflows has some significant downsides as well. So if you want to build a workflow management system by yourself, it's really hard to do it properly. There are a lot of pretty hard architecture decisions that you need to make. It might require skills that, just like, I don't know, like web development skills that maybe you don't have. And the hard decisions are, for example, okay, so the example is you have an optimization loop, right? So you have like many iterations, and in each iteration you perform like a couple of steps. So let's say you will evaluate the cost function, you calculate the gradients, and then you update the parameters. So these are like 3 steps. You know, it might be more. And what we wanted to do was, right, like what we had was this, the whole optimization loop was like inside a single task. And what we wanted to do was to actually divide it in like several tasks and like run them in a loop. And we created this architecture, and we, we're thinking pretty hard how to make it really work well. But in the end, it turned out that actually the overhead connected with initializing each task is so big that the calculation that, was running in a single task for a couple of minutes was running with this new optimization loop for an hour. So the overhead was really big, and like clearly we made some choices that were not optimal along the way. So it's not always straightforward to actually structure, in some cases, it's not straightforward how to structure your code in the way that like can best use workflows. Also, well, it just introduces an additional layer of complexity. So there's like more code, there's like more dependencies actually, because you also now have to deal with the workflow manager. And it's sometimes frustrating because instead of actually running your calculations, you're dealing with like why the scheduler doesn't work or whatever. Even though I said that, it's like it makes your thinking easier and it like forces you to structure your code and so on. And actually, there's still place for bad code and sloppiness. So it's not a panacea. There might be some execution overhead from the workflow management, because if, for example, as in case of Orquestra, you want to perform each task on a separate Docker and separate container, you have to initialize this container for. So if you are running like some very quick calculations, very small, it actually takes longer to run it using workflow than running it locally. And the last thing is that, this is like just another thing to learn. And, you just need to learn how to write workflows and how to like manage the workflows and how to run them. So that's not the, the knowledge that you necessarily need. But in general, I think that like the rule of thumb for me is that using workflow makes sense if your project is big, if it spans for months or years, or if you have like a huge team working together. But it might not be the good idea if you want to just do like some super quick exploratory research, or you have like some small project that you want to like quickly finish. Then, well, if you know given workflow management system, then like, yeah, that's good. I mean, but if you have to learn everything from scratch, that might be just too much of the overhead. And just quickly, I would like to for those of you who are curious, like what technologies do we use here? Well, we use Python. Like all the scientific code we have is written in Python. We have Go, and most of the infrastructure is written in Go. Then there's Argo and Kubernetes. So Argo is an open source, basically workflow manager. So it takes your workflow file and creates all the tasks and like schedules them and makes sure it all runs. And then Kubernetes is something that Argo talks to Kubernetes, and Kubernetes creates containers and makes sure you can run your code on a cluster like efficiently and like seamlessly. And there are a couple of other technologies that we are using, like S3 for storing data, Elasticsearch for logging, and like Conquers for some pipelines, and CI/CD. So, just like FYI. Okay, so that's enough for about the workflows. So now I would like to tell you about another concept, which is Python interfaces, and that we also like. I think it can really help in doing, especially in quantum computing, in performing research. So just I'll drink a little bit of water and tell you more about it. Okay, so there are several challenges we are facing, at Zapata every day. So for example, how do I run my circuit on any backend? It's pretty hard problem. Another question, because I already mentioned that. Another is, how can I utilize different pieces of code from different libraries? So we don't want to reinvent the wheel. So for example, if one framework already has a good method for example, Jordan-Wigner transformation, then we don't want to rewrite it. Or if you have a code which actually generates you a QA ansatz, then perhaps you want to utilize it and not write it from scratch. Well, how we can assure that like code base won't turn into spaghetti? So the problem is that if you have a lot of people working on something, then it might be just like hard to make sure to make sure that the quality of the code is good, and we don't want it to deteriorate. Then another thing is like how to avoid code duplication, because sometimes, for example, with the circuits, you might want to use like different backends, but they all share some logic, and like how to make sure that we, if we want to improve it, like improve it in all places at the same time. It's like not always trivial. And also another thing is making, like quantum computing is like a really vast field, and you might have a person who is expert in error correction codes, but actually doesn't know that much about like variational quantum algorithms. Or you might have a person which is an expert in quantum chemistry and can understand like this part of the experiment very well, but actually when it's comes to like circuit compilation, they have no clue what's happening there. So there are places that you want to make your code easy to use and like understandable for people, no matter like what's their level of expertise, and whether like if they're beginners, they should be able to use it without, you know, learning too much, and just like with default parameters, and make it like easy for them. But at the same time, when you have someone who's an expert, you want to give them enough flexibility so that then they can actually use their expertise and their knowledge to make it run really well. So the solution for these problems, to some extent, are interfaces. So what are interfaces? So interface is a Python class, usually an abstract class. Basically, when it comes to interfaces in different programming languages, some programming languages have interfaces as a part of the programming languages. Python doesn't have that. So that's why it's not, there's no like Python keyword interface. So it's just an abstract class. And this class has, you're going to have other classes that inherit after this base class, so that implement this interface, and they all will have common arguments and common methods, and as well common inputs and outputs from this methods. So it's much easier to ensure that, you know, if you have, for example, I will give an example of backend, because like, so quantum simulator, because that's like fairly basic one. So if you have two simulators, you just want to make sure that, like, even though, let's say, Qiskit simulator returns something in one format and PyQuil simulator returns in the other, you want to make sure that in your code they will both actually be in the same format. So if one is list, then the other is dict, to make sure they always return you the one format that you have in your code, so you can use them like easily together. And also another thing that might be pretty useful is that you can have a common set of tests for all classes implementing given interface. So for example, if you want to implement a new backend, you already have a set of tests that this backend should pass. So it's like easier to control the quality of the code. So this might be a little bit abstract. And so I'll give you an example, but before, well, there's this, you know, issue in software engineering that if someone wants to find a silver bullet which solves all the problems, they actually are just like kind of adding a new standard, and, you know, there's like, we have more standards. So we are aware of these problems when designing these, and are trying to actually not fall into this trap, but that's like, I put it here as a cautionary note. So an example of the interface and how you can use it. Okay, so let's say we have method which is called run circuit and measure, and we want to run a circuit and then measure it. So we have right now in this example, we have two platforms, so Forest and QLAX, and this function takes a couple of arguments, you know, circuit, platform, device name, number of samples. And as you can see, like, you know, we have one function, one method, which actually works for two different platforms, and it's pretty good idea for structuring the code the way it is. Because if we want to compare these two simulators, we can run it with following parameters, and we have Forest bit strings, and then with some other set of parameters, we have QLAX bit strings, and we can compare them or whatever. Well, it looks good when we have two simulators, but then someone comes and say, okay, but I want to add a new simulator. Well, you know what they do? They create a new simulator and they say, like, my own simulator. And then they say, okay, so I want to take circuit and, you know, I have some translate to my own simulator format, and I have this circuit, like my own circuit. And then I want to add some parameters for my simulator. So let's say my simulator takes as an input some noise models. So I will take the simulator and do, so results, my own. So results is equal to, you know, my own, like I will do MOS simulator, run circuit using MOS, and I will run circuit, and I will say, okay, noise model, but I don't know what's the noise model, so I will add, you know, like noise model here as an additional parameter. And let's say I call it, I don't know, like basic. And then, okay, so I pass it here, and that's cool. And then I have to translate it. So I say bit strings, or actually, let's say it's actually in the right format. So I can just like return bit strings. Okay, so I just, you know, need to add this code, but then it turns out that I have introduced additional parameter here. I actually need to write this code in this function in this place. So if I want to implement 10 other simulators, I will just like this function will grow. And let's say that actually Forest is using also noise models, but it uses a different format of noise models. So, you know, I have to take that into account, and it gets pretty messy. So what we can do is we can create different classes for that. And the different classes will implement quantum simulator like base class. I will show you the definition in a moment. But basically, we have a new class, which every class has run circuit and measure. And as you can see, the logic here is basically the same as it was. It can take different initialization arguments, and that's like not a big deal. They will be handled differently. So, you know, run circuit and measure in Forest looks like this. And then like finally my code will look like this. So I'll take backend and like instantiate an object. And then no matter what backend I have, they will all have this run circuit and measure method that will take a circuit as an input. So, you know, it will work. And if I want to add a new simulator, well, I will simply create a new class, and this new class has no idea about existence of all the other classes because it doesn't care. So it solves a lot of implementation problems for me. So now I would like to show you how such interface can look like. So we have an interface called quantum backend, and it has an abstract method which is run circuit and measure, and some others as well. And we specify, you know, what arguments it can take. And also we have quantum simulator, which, you know, inherits after quantum backend. So each quantum simulator has also run circuit and measure function, right? But as all quantum simulators have also like get wave function or get exact expectation values function, and like some others as well. Another thing that's like worth pointing out here is that if I tried to use, you know, if I created my own simulator here, oh, I tried to save it. So if I try to my own simulator here, and I forgot to implement the run circuit and measure, and then I would try to run it, well, I will get a not implemented error, which is kind of pretty obvious error message that, well, this is just not implemented. And in this case, I might get some weird error because, I don't know, like the type of the return type might be wrong, or there will be some error message like somewhere inside here, or even otherwise, like I might have handling errors and exceptions all the way in like each of these ifs, and like each of these ifs will look just like terribly when you add all the kind of assertions in here. So that's an example of an interface. So basically the benefits of using interfaces. So the first one is uniformity. So you kind of make it easier for people to have uniform way of using interfaces, like using, for example, backends. You have much better clarity of code because all the logic connected to handling Python simulator is inside Python interface, right? Like PyQual simulator, or regarding a QLAX simulator is inside this class. So it's just like clearer. The modules are independent from each other. So basically you can, there's like the only dependence, like common dependence, is on the base class, but that's something that you actually want. And it's actually, in some cases, this is something that I kind of discovered by accident. Like it's easy to add new features because let's say I want to add method which is called get expectation values for circuit set, where I don't pass like one qubit operator, but one circuit, but like a list of circuits. And well, then I can just write it in the base class, and it has basic logic like this. So goes through all the circuits and just run, get expectation values for them. But I don't have to implement that for like every single code. I can every single class I can just implement it in the base class, and then it's like gets propagated to all the other classes. And well, it works pretty well with the workflows, so that's also nice. I also wanted to point out that I used backend as an example because it's like I think it's like pretty basic example, but we have many other interfaces that we are using. So for example, we use interfaces for cost functions, for optimizers, for ansatses. So that's a nice abstract, like nice method for creating abstractions that is pretty useful in different places. So there are some downsides of using interfaces. So when it comes to implementing existing interface, well, there are basically no downsides of that. So the only downside that I can think about is that it forces you to use, the same methods and the same like input output data that you have. But actually, if you want to implement it, it's just, it's relatively easy to do that, and it's not like huge overhead. There are some downsides when it comes to like actually creating a new interface. So it takes time. And for example, when we're creating the interface for the different ansatses, just getting a good idea what should go into such interface and what should be handled by like some other classes, like some like inherited classes. Thinking what should be the methods of such interface, how to handle like some technical issues. It took about a week of just like discussing with people, like creating some basic prototypes to come up with this. So it takes time, and it also requires expertise, because if you, for example, are using if you just started doing quantum computing and you've never run like a lot of calculations and you want to create an interface, you might miss some pretty critical things in the designing phase, or you might just like design it very poorly, and it can actually lead to doing more harm than good. So because if you have poorly designed interface, it, instead of solving problems for the user, it might just like create more problems, because it will be very hard to implement something. Okay, so that's it. Now I would like to summarize what I said. Going back to like the title of the talk, because I know I touched like a lot of different things, but the first part, so using workflows in quantum computing. So it helps you organize your code better. It reduces a lot of dependencies. It is really, I think, a good fit for NISQ algorithm, for variational quantum algorithms, because they are, in many cases, naturally easily expressed as workflows. So, perhaps it might not be good for like some other algorithms or some other methods, but in NISQ, you have so many different pieces that need to work together, where like quantum computers is like one piece of that. Then you have like optimizer, you have to prepare a Hamiltonian, you have to post-process the data, a lot of different things. So it really works well for NISQ. And using workflows really helps with collaboration. Like much easier to share your work if everyone in your team uses the same, or in your like company uses the same workflow system. And if it fits Orquestra, if the workflow system you are using is Orquestra, well, it actually has a lot of other additional benefits that I wasn't talking about. So like managing the output data, like putting into the database, and Orquestra is pretty good. So it has like some other useful features. So, and how good software engineering helps in doing science. So apart from like all the other like points I made, if you have well-written code and you want to share your research with others, if the code is well-written, well-documented, and easy to use, then others will use it. There are a lot of projects with very poorly written code that no one uses because it's just like too hard for others to like get through the code and figure out what it's doing. So just like making sure the code is good can help to spread your ideas. In general, a little overhead right now will save you a lot of time in the long term. So it's often worth to not just like go rush and start coding, but actually think what you plan to do and spend some time, implementing it in a harder way, like more difficult way, but the one that like is more scalable. Code that is well written is like just easier to debug. For example, the don't repeat yourself principle really helps with that. Good abstractions make thinking process much easier. So like if you don't need to, think about all the connections that specific function has, and you don't have to kind of worry about how changing this one method here will break something, 4 layers of abstractions above, and you have it all modularized. It's just like thinking is easier. And it allows you to focus on the science and not on the code, because you don't have to deal with, if you have like less bugs, if you have clearer code, you can just like focus on what's important and like actually doing science instead of dealing with all the issues of the software. So thank you very much for listening. A couple of links. So, well, I invite you to visit the Zapata website. There are some interesting materials there. There are some blog posts that also are like about similar things. I have my own blog called Musty Thoughts, so I write about quantum computing and other stuff as well. So I invite you there. And also a lot of code that we have is open source on GitHub. And if you would like to see, for example, how the interfaces work, go there and you can check it out, how all the different repositories work together. And if you have any questions, you can, we will be talking now, but also you can send me an email. You can find my email on the blog. I forgot to put it here. But yeah, I think that's it. So are there any questions? And I think there are on the chat. So I'll just go through the questions from top and start answering them. Okay, so when you had a problem of not knowing which version of the code was used for a particular output, would it have worked to create a new directory for the output files each time? I mean, so this is an issue that creating a new directory output each time I modify the code requires me to actually keep track of that, and like it requires a lot of discipline for myself. And yeah, it is a way, and you know, you can do that, but it actually doesn't solve like the bigger issue. So can you elaborate on the algorithm high level? So I was mentioning some algorithm when I was talking the story about like estimate and how I screwed up something here. No, I can't. It's like, I mean, it's secret, right? Like I can't tell you details about this algorithm. Could you comment if the process and culture list, could you find if you found any of these items especially challenging in a corporate environment where different tasks are done by different teams sometimes? So actually, I have to say that in Zapata, we don't have like super big team. We have like, I don't know, 30, 40 people, something like this. And I don't know, like some of these principles I listed there, they work well. One of the things I like about workflows is that sometimes I was helping with different projects, and you know, people from other projects ask me to, you know, implement this specific function or like this specific method of, I don't know, calculating radians or whatever. And since the code is modular, since you know we work in this workflow system, I actually didn't need to understand the whole algorithm and the whole project. I just needed to understand enough to be able to implement this one part. So that was helpful. It's not really about process and culture. Wait, I will go back to this list and just like see if I found anything particularly challenging. So the list is here. No, I don't know. Like sometimes there might be some issues with like, you know, like people issues, but it depends on like specific situation, I guess. About teamwork, any comments on value of participation in hackathons? Any comments on explicit collaborative programming tool like Google Doc or for writing? So I know some people in like another team are using Zapata are using some of these like collaborating tools. I personally never use them, but they like it. But I don't have much more to say about it. Regarding value of participation in hackathons, oh, like I really love hackathons, and I think it's like a lot of fun and allows you to learn very quickly, very efficiently. Actually, you know, hackathon code like defies all the good kind of good practices that I was talking about, because usually are super short on time. So there's like no time for like polishing, writing unit tests and stuff like this. But yeah, I would say that like participation in hackathons, it's really a valuable experience, and I highly recommend it to anyone who, if you haven't done it yet. Everyone is going the VQE route for the bond length. Is there any other method anyone knows to do molecular or quantum chemistry or quantum field theory with a quantum system qubit? So except the VQE, well, I don't know. I'm not an expert in quantum chemistry. I think you can do something with phase estimation, I guess, but I'm not sure. But phase estimation is not very like NISQ friendly as far as I know. Also, I think there is phase estimation is described in a nice tutorial by David Hachatrian. If you send me an email, I can send you a link to that. What is your opinion of the workflow management system called Pipeline Pilot? I have no opinion because I don't know that system. Then like, seems everyone except for Q# is making use of Python. That's not entirely true. There are some, for example, simulators in Julia or in C++. maybe some of them have Python interface, but not necessarily. Yeah. But yeah, it's a valid point. Extendable modular quantum language is Sanskrit. So, and here is a link, okay? Okay, if one useless classes for custom. So, Veselin, you made this point about useless classes for custom built neural networks. I don't get it.
Well, I wanted to point out that actually what you were saying for the interface is really a very useful way. But I had experience working with somebody on neural networks, and they didn't put from the beginning the save function to save the model and the state of the training. And it was okay when we were training on small data sets and when we didn't have to wait to restart or things like this or crashing. But as soon as we start running on big data sets, then not having the standard kind of, most of the models, when you look at PyTorch and TensorFlow, they'll have an automated save option. So we can save and then start again. But because he was doing his classes, his own custom neural network, he didn't build it. So then we had to step back and spend about a week to figure out how do we code now saving the state so that we can restart the training later and continue. I think the point is basically back to talking at the beginning what you're gonna do and what is the workflow, because these are things that can kind of push you back if you didn't anticipate or you didn't try to do something that you were anticipating and say, I don't need it. And I say, oh, I knew I needed that.
yeah, that's definitely true. And it's also like, I think it's in general, it's in most cases, it's better idea to use existing frameworks because there were a lot of people working on that and they probably had a pretty good idea of like what features you need and what features are really important and not like reinventing it again. So yeah.
I agree with that. I mean, first you have to try to see what is out there. Can you adapt? And if it works for your purpose, then there is no need to spend more time to develop something new. If you don't find what you need, then you have to try to figure out what you can adapt.
Yeah, exactly. So a question from Bombardé: do you think engineering schools should update their software engineering curriculum to help bring students up to speed with modern industry software engineering best practices? Absolutely. So, I mean, the principles, I think principles didn't change too much in like last, I don't know, 10 or 20 years. It's like some tools changed, but definitely when I was at the university, they didn't teach me too much about like good practices and like how to write good software. So yeah, I really think people should pay like more attention to that. Especially like not especially, but on like not computer science kind of courses as well. So like if you're studying physics, you also should kind of just get a little bit of good practices because in the end, like software will be one of the major tools you'll be using in many cases.
And I wanted to comment to Bombardé's question. Actually, like everything, some pluses and could be turned in minuses and vice versa. And the case that universities are very slow to adopt new computer standards actually brings the opportunity for entrepreneurs and startups to build their own training curriculum. And I know like a Bitwise nearby in Fresno, there are few companies in San Francisco that are training actually how students to do a better programming and go through this kind of special like apprenticeship schools. Eventually, I mean, this would become a widespread and probably academia would adapt eventually. But it's opportunity for small companies to make a big contribution.
Yeah, that's true. Also, there's this issue that I'm not sure how much of good practices are you able to really kind of teach. in the sense that, unless you really make this, unless you make the mistakes by yourself, it's like sometimes really hard to appreciate the value of this, of these problems. But still, I think like people should try.
Yeah, I think one option that university can do it if they incorporate it in their culture, because you have a lot of homeworks to do and things, but if these good practices are observed by the teachers and the TAs, then naturally becomes taught through the course.
Yeah, thank you. So this is my second semester in Zapata University. So this first one was more theoretical. This session was more practical, and see the code review, those simulator and circuits. So that was very interesting, this talk, and we would like to see more of Zapata University's training. It is almost like covering a university course. So we are expecting the next topic will be on hands-on something, or more theoretical, or a mixed one. Is for Michael.
I mean, you mean what would be next theoretical?
Yeah.
So I didn't get it.
Is it going to be a practical like this one, or kind of a mix of more theoretical and?
Yeah. I don't know. I mean, I'm not involved, so
Okay.
not sure. Sorry.
Yeah. So yeah, it was very useful in the sense it's progressing in a more simple to complex one. So yeah, I would like to have your next talk in a monthly basis. Is it possible?
We'll see. I mean, vacation are coming, so that's probably not a good. Might not be good time, but in future, probably yeah.
Okay.
Well,
yeah, whenever you find time, yeah, please.
Sure.
Thank you very much,
Yeah.
Michael, and thank you everyone that attended today's seminar. I think it was very useful for people to see what they're getting into if they're planning to go into computer science and specifically in quantum computing. And hope some people would really decide to go that route.
Yeah.
Bye.
Thank you very much. Have a nice weekend, everyone.
Yeah, it is recorded.
Bye.
So I'll post this link in the website. Meet up later.
Thank you, and have a safe weekend. Great job.
Thanks.
Mike.